Okay. Okay, so I have a couple of announcements before we get started. Um, so I have your graded homeworks here. I'll return them at the end of class. Um, and then we have another homework out, and it'll be due next week. So, homework 2 is out. You can find it on the website. Um, and it will be due Wednesday, that is 3/18/2020. Okay, so we have a week and a half to get it done. I suggest very strongly that you start right now, so that you can take advantage of the office hours between today and when it's due. There's also a computational activity. We're going to complete the classification with Euler curves activity that we started in class. The code is pretty slow, the one that we gave you in class. So again, start early so that you can debug and optimize the functions that we gave you. So that's that. So let me get started. So we started with this idea of, at least before the break, this idea of simplicial maps and they're induced. So let's say simplicial maps, F from K to L, where these guys are oriented simplicial complexes, meaning that we've chosen an orientation of each one of the simplices. We have their induced and their induced linear maps. F sharp from the chains Z to the chains of L. And I have to tell you how these guys are defined. So the sharps, the way we did it was, if we take, so you want to send sigma to F sharp of sigma, where this is an n simplex. So the way it is done is that if n is, say, u0, u1, all the way up to un, then F sharp of sigma is given by the following two choices. It is either 0 if the dimension of sigma is bigger than the dimension of F sigma. Right, so if you lost, so I mean, remember that when you apply a simplicial map to a simplex, you can reduce the dimension because things can get collapsed. So if the dimension is reduced, when you do that, then you get 0. And if not, you get -1, not -1, but the sign of pi, and I'll say what this is in a moment, times F sigma, where so we need a couple of notational devices. So where F of u0, u1, un, and remember that when I write brackets, I want to emphasize that the simplices are oriented. So this is equal to v0, 1, jn. Pi is the collection of indices, and this is seen as a partition, as a permutation. right? And then the sign of pi as a permutation is -1 to the number of inversions. And we defined it sort of loosely as the number of inversions. So the inversions, number of inversions of pi is sort of the number of flips that you need to do to put this permutation in order, in increasing order. Another way to think about it for the ones that know a little bit more about permutations is that any permutation can be written as a composition of transpositions, and then the number of partitions, the number of transpositions that you get in the expression is either odd or even. So that's what you put in here if you want to think of it that way. Right. So that's how we define the sharps at the level of chains, of n chains. So you define it first just on n simplices, and the way you do that is by either 0 or plus or minus 1 f of the simplex, depending on whether or not you keep dimensions. And the dimension, and then plus or minus 1 is defined by this expression. We also showed that if you let f sharp act on cycles of k, then that gives you cycles in L, and that if you act via f sharp on boundaries, then that also gives you boundaries in L. And the way we showed these two facts was by checking that. So this follows from by the following fact, that if you look at I guess n minus 1 here, n minus 1, so there are two things you can do. You can take boundaries, or you can look at the sharps. And what we showed was that going this way, meaning applying f sharp to delta n of L, delta n of k, was the same thing as applying delta n of L to the other sharp. So from this formula, one can see that f sharp sends cycles to cycles, boundaries to boundaries, and this allows you to define the f star. So we can define the f star, and this is now going from the homology of k to the homology of L. And the way it is done is it takes the class of a cycle, and it says the following. The first thing I'm going to do is I'm going to take this cycle, and I'm going to apply f sharp to that cycle, right? And from here, we know that if you apply f sharp to a cycle in k, you're going to get a cycle in L. That's the first thing. And then the second thing we do is we take the homology class of this new cycle. That's it. And the second fact, that boundaries go to boundaries, tells you that, that this is well defined. That if you pick another representative of this class, you're going to get the same class in here. Okay. So that's essentially what we did before the break. Sort of the idea of the f sharps and f stars that come out of having simplicial maps between simplicial complexes. I want to do several examples today, just to illustrate this machinery, then we're going to see that using the integers here can become problematic for the things that we want to do. And then we're going to change these for something a little bit more conducive to algorithms. And that's what persistent homology is going to give you. Okay? So that's the plan for today and Wednesday. Okay. So again, let's just start with a bunch of examples and see what we get. Okay, so the first example I wanted to do, we're going to start simple. Okay, so the first example is going to be the following. I'm going to take K to be this guy, and then L is going to be this guy here. Okay, and I'm gonna let F be the inclusion of K inside of L. So every time I write an arrow with a curl at the beginning, is to indicate the inclusion. And what is the inclusion? Well, if I give no names to these guys, so U0, U1, U2, then this is going to be U0, U1, U2, and U3. Then U0 goes to U0, U1 goes to U1, and then U2 goes to U2. Okay? So that's what the inclusion is. It's just the simplicial map that takes whatever I have in here to the same thing in here. Okay? So L just has to contain K. It just has to be bigger than K. And then the inclusion is just sends whatever I have in here to the same thing in here. Okay? And you know, we orient the complexes in the usual way. And then U2, U3. Okay? So let's start slow, as I say. Okay, so let's start by giving names to some of the cycles that are of interest in here and here. Okay, so let's take, for example, zeta. I'm gonna let it be, U0, U1 plus U1, U2, and then minus U0, U2. Okay, so zeta is, going down like that, and then going up. So it's this cycle that is sort of characterizing this hole in the space. Okay, so, yep.
Why didn't you
I could have, yeah, I could have. I'm just, is this sort of notational inconsistency of wanting my simplicial complexes to be sets, but to be a collection of sets. But you're right. If I wanted to indicate that the order matters, I would have put brackets in here. But yeah, it's just a notational inconsistency that I'm going to commit shamelessly. So that's the first cycle that I'm going to think about. So hopefully we can see that if you compute the first homology of K with coefficients in Z, then this is exactly isomorphic to Z. And again, just to remind ourselves what this notation is telling you. So he's saying that once you compute, right, so let's see how would you compute this guy, right? So first you have to compute what are the cycles in K. So any cycle in here is going to be a multiple of zeta, correct? Because it has to satisfy that the value that when you take boundaries, right? So the value in this edge has to be the same as this value in this edge, and the same as the value in the edge going that way for the boundary to be 0. Okay? So any cycle has to be of a multiple of these guy. Okay? And there are no, and then you ask, okay, what are the boundaries? There are no boundaries because there are no two simplices. Okay? So this is exactly what the homology is. Okay? And one way to read this is that zeta is this cycle that we chose. If I take 2 zeta, then what that would mean is going around zeta twice, 2 times. If I put here -3 zeta, then it would go 3 times in the opposite direction. Okay? So the n is just telling you sort of the number of loops that you're taking along zeta. Okay? So again, in that sense, we think of zeta, I'm going to put it here, as the number 1. Does that make sense? Sort of zeta is sort of the cycle, and the way to pair cycles in here with the integers is by telling you how many times I'm going around the chosen cycle. Okay. Now, let me give you another cycle. I'm going to take zeta prime. So zeta prime is now going to be u0, u2 plus u2, u3 minus u0, u3. Okay? So that cycle is the one that I have here. Okay? And again, hopefully we can see that h1 of L is all the multiples of zeta prime and in here we're making zeta prime be the corresponding 1. Okay. Now let's try to think about the F star induced by F. Okay. So we want to think about F star from H1 of K to H1 of L. And I would like to remind you that this is Z, where we're putting zeta in correspondence with the number 1, right? So going around zeta 1 time. And here, this is also Z, but here we're taking zeta prime and making it our number 1. Okay. So if I want to know what F star is on every element in here, it is enough to check what happens to zeta. In other words, to 1. Okay? So let's do it over here. Okay, so by definition, F star of the class of zeta is what? It's the same thing as taking the class of F sharp of zeta. That's how we define the stars in terms of the sharps as we did before. Okay? So in other words, I'm taking the class of F sharp of u0, u1 plus u1, u2 minus u0, u2. So let's see what happens. So when you take f sharp of 0, 1, you go back to the definition of the simplicial map, and you see that 0, 1 goes to 0, 1 is the inclusion, right? And there are no flips in the orientations. So this is the class of 0, 1, plus, you go back again, 1, 2. 1, 2 goes to 1, 2. And the same with 0, 2. Okay? So nothing fancy has happened yet. Now the thing to realize is that this cycle, the cycle 0, 1, 1, 2, 0, 3, 0, 2, in L, right? 0, 1, 1, 2, 0, 2 is the boundary of this simplex. So this is the boundary in L of 0, 1, 1, 2. Okay? And this is 0. So in other words, F star sends the generator in the homology of K to 0 in L. Okay? So I guess the way the way I'm going to write that down in here is saying that my generator 1 is going to 0. Okay? So again, the generator is zeta, and I showed that F star sends zeta to the class of 0. And hopefully, this algebraic exercise is consistent with the geometric picture that in here I have the cycle zeta, but when I go to L, that cycle has been covered, so the whole disappears. Okay? Are there any questions that I can clarify or expand on? No? Okay. Let's do another example and see what happens. We're going to get a little bit more ambitious now. And instead of just 2 complexes, we're going to take several. So here's the second example. We're going to take, so K0 is going to be the square. And I'm going to take K1 to be this guy. K2 is going to be this guy with this filled in. And then K3 is going to be this guy with both sides filled in. Okay? And the simplicial maps that I'm going to consider are going to be inclusions between every 2 consecutive Ks. Okay, so what I would like to do now is I would like to compute the homology of each one of these guys. Okay, so I'm going to compute homology in dimension 1 of each one of these complexes. Okay, so here we have one hole, so that should be Z. Here we have 2 holes, so that should be Z cross Z. Here we have one hole again, and here we have no holes, so this should be 0. Okay, and then what I want to see is what are the stars at the level of homology that I get. Okay, so here's something interesting. When I write zeta cross zeta, is because somehow I found a way to identify the cycles in K1 with pairs of the form n comma m. Okay, so before what I did here was identify every cycle in here with an integer. Okay, so when I say zeta cross zeta, perhaps I should get specific on what I mean. Here in zeta, there is sort of not much choice. So zeta, I'm going to take it to be generated by this cycle. Okay, so that's going to be zeta. And so here, when I think of this guy, I'm thinking of all the multiples of this zeta. Okay. When I look at this guy, I have several choices, but one choice to make would be, let me take this guy as my first zeta, and let me take this guy as my second zeta. Okay. And in here, I guess the choice would be that. This would be my zeta in here. Let me call it zeta prime. So when I say z cross z, what I'm really saying is that I have things that look like pairs n zeta 1 plus m zeta 2. And here n and m are in z. And in here, I'm saying that I have things that look like, let's say, k zeta prime, and then k is in z. Correct? Okay, so let's see if we understood how the stars operate at this level. Okay, so let's say that we take my 1, right? So 1 in this case would correspond to zeta. Okay, so where does this guy go in terms of zeta 1 and zeta 2? Any guesses? Yep. Zeta 1 plus zeta 2, right? Because it would be zeta 1, that would be this guy, and then plus zeta 2, it would kill this diagonal and get you the other one. Okay, so zeta 1 plus zeta 2 would be what? 1 comma 1. Correct? Okay, cool. So now that we're here, you can look at 1 comma 1. So where does 1 comma 1 go in here? So as we saw, this is the one that we did before, right? Where this guy went to 0, right? So 1 comma 1 goes to 1, right? And then 1 goes to 0. And then we're missing another basis element. So let me say what I mean. Every pair in here can be written as a combination of 1, 1 and another basis element. We haven't specified what that other basis element is, okay? But let's say that I did, I don't know, 0, comma 1, okay? So that's another basis element, correct? Where does 0, 1 go? It goes to 1 as well, right? Because this is the class that I'm keeping, okay? So there is a conundrum in here, in the following. So he's saying that I have sort of a class, I have a hole that starts here and then sort of survives all the way up to here, okay? And then another hole appears in here, right? And it continues, meaning that 2 holes continue? No, he's saying that the 2 holes that I had in here sort of combine into 1, okay? So the way, or at least one way in which one can disambiguate this choice is by something called the Eldar Rule. So let me say what that is. this is like a folk name or something. It's called the Eldar Rule. And what it is keep the older class. Keep the older class, kill the younger one. Right? So that's what it is. So another way to think about it is, of course, this way of looking at these maps depended on this choice of bases, correct? But we can do another basis choice, correct? So, for example, we could say, let's see, what's the one that I chosen here? Yeah. Okay, so another choice of bases, right? Would be, take 1 going to 1, 1, and then this goes to 1 and then 0. And then the second element that I can pick in here can be 1, 0. Right? This is another element that when you combine it with this guy, you get another basis. It's different from these bases, but now the effect that it has is that when I look at where it maps, it goes to 0. Okay? So in that sense, we kept the older class and killed the younger one, and we did that by a appropriate choice of bases. Okay? So this is the key idea of persistence, at least in my head, is that, and I'll say it here, and we'll keep repeating it as we move forward. So the idea is what I'm gonna call the consistent choice of bases. Again, super important. This is what I'm gonna use moving forward. And it's the idea of you want to pick basis elements in each one of the homology that you've computed. Maybe this has another guy in here. In such a way that a basis element either goes to another basis element or the basis element goes to 0. Okay? That's what happened here. I made a specific choice of bases in which a basis element went to another basis element or to 0. Again, this is going to be the key idea of persistence. Pick bases in such a way that a basis element either goes to another basis element or to 0. Okay? It'll make more sense as we move forward, but again, this is the key. And what this allows you to do is to keep track of how the homology is changing, right? So it's saying that this homological feature is going to this homological feature, and then it's going to this homological feature. So that's how you pair homology across scales, at least, by making this consistent choice of bases. Let's do another example. Which one should we do? Let's do dimension 0. So this is going to be a little bit simpler. So K0 is just going to be U0. I'm going to include that into K1, which is U0 and U1. and then I have K2, and I'm going to put the edge. And let's compute H0 for each one of these complexes. Correct? So remember that H0 is measuring the number of connected components of the space. So in here we should get Z, Z cross Z, and Z. Okay? And let's look at the induced maps by this inclusion. Okay, so again, when I say Z, I have to say what I mean. So here I'm saying all the multiples of U0. That is the only zero chain I have. In here, I'm saying, let's say NU0 plus MU1, and N and M are in Z. And in here, I can pick either one, say U0. Okay? Okay, so with this choice of bases, I have that 1 goes to 1, 0, and 1, 0 goes to 1. Okay? So I could choose another basis element, like 0, 1. Okay? And in that case, 0, 1 would also go to 1. So you're back in this Eldar Rule question where you want to pick the class that is older and kill the class that is younger. And again, that refers to a choice of bases. Okay, so so I think one choice of bases that would work in here would be, let's say 1 minus 1. Right? So this is certainly another basis for this space. And this now goes to 0. Okay. And we have a similar behavior, that's what I explained here, that by, again, picking appropriate bases here, I can pair generators with generators. And see how the homology persists across the different complexes. Great. Let's do one that is hopefully a little bit more complicated. Okay, so for the next example, we're going to do something a little bit more complicated. So I'm going to take K to be a hexagon. You know, U0, U1, U2, U3, U4, and U5 with the usual orientation. And then my L is going to be the triangle with vertices V0, V1, and V2, and then the orientations as usual. Okay? My simplicial map, F, at the level of vertices is going to be given by Uj is going to go to U, is going to go to V. I'm going to take J mod 3. Okay? So in particular, U0 goes to U0, to V0. U1 goes to V1. U2 goes to V2. So notice what I'm doing. So U0, U1, U2, V0, V1, V2. So we already covered one loop. And then when I say U3, that goes to what? V0, right? 3 mod 3 0. Then U4 goes to V1, and then U5 goes to V2. So essentially, I'm going one time around this hexagon, and then I'm going 2 times around this triangle. Okay, that's what the simplicial map is doing. Now let's think about F star at the level of the first homology group. And I think it'll be useful to start with cycles in each one of these guys. So here I'm going to take zeta is going to be the typical. So U0, U1 plus U1, U2 plus U2, U3 plus U3, U4 plus U4, U5, and then minus U0, U5, and then zeta prime is going to be V0, V1 plus V1, V2 minus V0, V2. Okay, so as before, we have that H1 of K with coefficients in Z is all the multiples of zeta, which in turn is Z, and then that H1 of L is all the multiples of zeta prime, which is also zeta. Okay, so as before, let's think about F star. And again, this is isomorphic to Z, where zeta has been paired with 1. And here, this is also isomorphic to Z. And then here, zeta prime has been paired with the number 1. Okay? So what I would like to ask you is, if you see what this is equal to. We'll do the computation if it is not apparent. Okay, so let's just use the definition and see what happens. Okay, so this should be the class of F sharp of zeta, again by definition, and let's just compute what this is. So we're going to apply F sharp to this cycle, okay? So now 0, 1 goes to V0, V1, 1, 2 goes to V1, V2, 2, 3 goes to 2, 0, right? So there's a flip in the orientation. So this is equal to 0, 1 plus 1, 2 minus 0, 2, right? And then plus 3, 4 goes to 0, 1 again. 4, 5 goes to 1, 2, and 0, 5 goes to 0, 2. So the same thing. Right, it's the class of that cycle, right? Which is nothing but the class of zeta prime plus zeta prime. In other words, is the class of 2 times zeta prime. Okay. So if you look at what f star looks like at the level of integers, right? What it's doing is it's sending zeta, which is 1, to 2 times zeta prime, okay? So again, another way to think about f star is by sending 1 to 2, or 2 times 1, rather, where 1 in here means zeta, and 1 here means zeta prime. In other words, f star is actually just multiplication by 2, which is what we thought from the start, because what f is doing is sort of looping around the generator 2 times, okay? So there are several things that are interesting about this example, even though it seems trivial. Let me start here. Okay. So hopefully you will agree that the f that I have here is a surjective function, right? It covers everything in its range, right? So f is surjective. But when you look at f star, you will see that it only hits the even numbers, right? It doesn't hit the odd ones. So f star is not surjective in particular. Right? Another thing to notice is that multiplication by 2 from z to z, right? You take a number and you multiply it by 2, that is certainly injective. Okay? So f star is injective. But now if you look at f is going twice around the same space. So f is not injective. Right? So what that says is that properties like injectivity, surjectivity are not preserved when you take stars. Okay, you could have started with a map that was injective, like the inclusion, but then when you take the stars, that may no longer hold. Okay, so this is an important example, and you're going to have some more like this in the homework. Okay. The last thing that I want to remark, and I guess is the most important one, is the following. If you look at what we did before, this idea of consistent choice of bases, right? Where you wanted to pick a basis element here, pick a basis element here, and see how those basis elements match, right? The thing to notice is that it is not possible to pick consistent bases between these two, right? Because the number 2 is not a basis element for z, right? You cannot generate everything in z by just multiplying with 2. You can only generate even numbers. It is not possible to generate 3, for example. So it is not possible to pick a basis element here, a basis element here, so that basis elements either map to basis elements or to 0. Okay? So in Z, it is not possible to pick compatible bases. Right? The thing that you would like to do is say, if only these guys were like the rational numbers, right? If these were the rational numbers and these were the rational numbers, then you're good. Like any number here will be a basis for the rationals, and any element here will be a basis for the rationals. The problem is that we're in the integers, and 2 is not a basis element for Z. Okay? So this is where the inadequacy of Z comes in this idea of trying to pair basis elements across scales. That you may get a basis element that goes to a multiple of a basis element, and it's just not possible to get that multiple out of the way. What you would like to do is you would like to divide by that multiple, but we can only do that in fields, like the rationals, the complex numbers, or the real. Okay? So we're going to switch gears now, and we're going to change this Z for a field. So this motivates homology with field coefficients. And again, the reason is because the integers were insufficient in this task of pairing basis elements. So let me remind you what a field is, and we'll go from there. Okay? So a field is a set F, so F, fancy F, or field, where one can do the following. One can add, so one can say like A plus B. One can multiply. And all the good things that come with this, right? So things are associative, commutative, and multiplication distributes over the sums, so distributive. So all the good things that we know how to do with numbers. You can add them, you can multiply them, things are associative, things commute, and so on. The other thing is that there are identities or neutral elements. So neutral elements, meaning that if you take A and you add 0, you get A. If you take A and you multiply by 1, you get A. And then so any A always has an additive inverse. And if A is not 0, is the additive neutral element, then there is a multiplicative inverse with A times A inverse equal to. Okay, so yeah. It's more, right? Because think of R2 as a vector space. Say that I gave you the vector 1, 2. What is the multiplicative inverse of 1, 2? You don't have one, right? So it's a little bit more than that. So I guess this is great. So I can give you several examples of what this is. And I'm going to do it in 2 columns. The ones that are vector spaces, sorry, not vector spaces, fields, and the ones that are not fields. Okay? So the typical example of a field would be the rational numbers, right? We can add fractions, we can multiply fractions. 0 is a rational number, 1 is a rational number. Any non-zero rational number has a multiplicative inverse. Just flip, and we're good. What would be an example of something that is not a field? The integers, for example, right? Because 4, the number 4, doesn't have a multiplicative inverse. Okay? Other examples, you know, the reals, the complex numbers, and here we can put our n for n, let's say greater than or equal to 3, because R2 is way too similar to the complex numbers. So let's say R3 and on. Okay, so that's what a field looks like. Something where you can add, multiply, everything is nice. Multiplication has always an inverse. And if you lack, usually the thing that you lack is multiplicative inverses, and that lands you in something else. Okay? There is another example that I want to use. Yes, everything commutes. Are not, right? So for many reasons. So even if you put like invertible matrices, like invertible n by n matrices, the fact that multiplication doesn't commute says that this is not a field, even if you have inverses. Okay? Yeah, that's a good example. Thank you. So there is one example of a field that I like very much and that computers also like very much. It is the integers modulo a prime. Okay, so as before, let P, or let n be an integer. Let's do it like this. So let n be an integer. Let's do it like n and z. Z, let's do n. Yeah, this is better. Let n be a natural number, and let z mod n be the collection of equivalence classes where L is in K, if and only if n divides K minus L. Right? So equivalence is modulo n. Correct? So for example, we have that, I don't know, let's say z mod 2. So z mod 2 would be 0 and 1. Z mod 4 would be 0, 1, 2, 3. That's it. Not yet. That's why I said. Yeah. So in general, Zn is going to be the class of 0, the class of 1, and all the way up to the class of n minus 1. That's how modulos work. Because now when you get to n, that is the same as 0. Because n minus 0 is divisible by n. Okay, so these z mod n's also have addition and multiplication. So z mod n has plus and times. And the way it is defined is that if you take two such elements, the class of K and the class of L in Z mod N, then one can let K plus L, one can define it as the class of K plus L, and the class of K times the class of L, one can define it to be the class of K times L. And one can check using just properties of division that these operations are well defined, in the sense that if I picked a different K in the same equivalence class, you will get the same equivalence class here at the end. Right, so for example, let's do C mod 4. So in Z mod 4, let's do the addition table. Right, so addition, and we're just gonna put the classes in here. The class of 0, the class of 1, the class of 2, and the class of 3. And here again, class of 0, 1, 2, and 3. Okay, so 0 plus 0 is 0, 1, 2, and 3. And you will notice that since the addition of integers is commutative, then the same will happen here. So this matrix is going to be a symmetric matrix. We don't have to do everything. So 1 plus 1 is 2. 2 plus 2 is 4, but 4 mod 4 is also 0. And 3 plus 3 is 2. 1, 2 is 3, 0, and 2 plus 3 is 1. Right. So that's the addition tables. I don't want to bore you, but I feel like I have to do it at least once. And then let's do the multiplication table. Times. It's the same thing. 1, 0, 1, 2, and 3. 0, 1, 2, and 3. Again, things are commutative, so the matrices are going to be symmetric. The table is going to be symmetric. So this is 0. This is going to be the same. And then 2 times 2 is 0, which is 4. 2 times 3 is 6, which is 2. And then 3 times 3 is 5, which is 1. Right? So there you have it. Addition and multiplication. And then hopefully what you can see is that, if you wanted to code this up in a computer, you can essentially have lookup tables that tell you how to multiply in these guys. Okay? And here is one feature of these spaces, of these Z mod N's. Notice that, let me take, for example, 2, right? And perhaps I want to fill up the row. So let's say this is 2, and this is 3. I want to fill up the row. So this is 0. Okay? So what I want you to notice in the multiplication table for 2 is that there are no 1s, right? There is no other element that when you multiply it by 2, you get 1. In other words, not every non-zero element has a multiplicative inverse. Okay? So in particular, Z4 is not a field. Right? So Z4 It's not a field. And the reason is because, for example, 2 does not have a multiplicative inverse. Right? There's no other number that there's no other element, sorry, that when you multiply by 2 would give you 1. Okay? So it's not a field. What one can check is that here's something one can check. Is that Z mod n is a field if and only if n is prime. Within a prime number like 2 and 3 and 5 and 7. So we go back to our example where yes field, no field. Then Z mod 2 is a field, Z mod 3 is a field, Z mod 5 is a field, but Z mod 4 is not, Z mod 6, Z mod 8, and so on. Okay? And these are sort of super simple fields that the computer can understand, right? So this is going to have 2 elements, 3 elements, 5 elements, and you can just code up the multiplication table and the addition table if you wanted to. Okay. So now we have a bunch of examples of things that are fields. We have the Z mod P's for P prime. We have the rationals, the reals, the complex. And we have also a bunch of examples of things that are not fields. The Z mod n's where n is not a prime. Like 4, 6, 8, and so on. Okay? Great. So now that we know what a field is, we can go back to homology. So homology over a field F. And again, F can be, the rationals, the reals, the complex, or one of these Z mod P's that are so useful. So what do? So we do exactly the same thing we did before, right? So we take K, so step 1, right? Fix your field and fix your complex. Right? Step 1. Step 2, we fix an orientation on the simplices of K, because we do that every time we want to compute homology. Okay. And on the simplices of K. Step 3, we're going to define the chains over F, over the field F, or another way to say that is with coefficients in F. Okay, and what is that? So it's exactly the same thing we did before over the integers. So we're going to let Cn, K, and now we're going to put an F in here. So hopefully now it's clear why I was so sort of bothersome with keeping the Z straight in here. It's because we knew that at some point we were going to change it. So Cn, K, F, so these are chains, n chains in K with coefficients in F. So these are what? So this is the set of functions, phi. So what is an n chain? when we had Z in here, so it was something that assigned to every simplex an element in Z. Okay, so that's where the integer chains. So now over F, this is going to be functions from, the n simplices to F. Right? i.e., if kn minus kn minus 1, so if the n simplices are like this, then phi is equal to, sort of lambda 1 sigma 1 plus lambda 2 sigma 2 plus dot 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 lambda n sigma n, where each one of these lambdas is an element in the field. Right? So again, just to bring you back to the things that we've seen before, when we were defining the chains over the integers, we were thinking of functions that to every n simplex give you an element in Z. Now we're going to give you an element in the field. And before we wrote our n chains as these linear combinations of the n simplices, and the coefficients were integers. That's what we had before. What we're going to have now over F is that our coefficients now can be elements in the field. Okay? That's it. But now we're in the linear algebra land, because now this is a vector space. So the remark now is that CNKF is a vector space over F, and the n simplices form a basis. So now all your intuition from linear algebra actually works in here. You can think of these chains as vectors, right? So in particular, if you think of a chain in terms of the linear combinations we had before, then a similar way to think about it is just as vectors. And now these vectors live in F to the n, right? So honest to God, n tuples. And all the linear algebra can be brought to bear in here, okay? Yeah, let me say the final two things and then or in fact, let me stop here actually, and I'll return the homeworks. So what is next? So now that we have chains over a field, and we have that our linear algebra now applies, then we can now think about the boundary maps as matrices. Now we don't have to do Smith normal form. We can do just Gaussian elimination because we can divide by things. And now homology is going to be also a vector space. Things are super, super nice. So that's the promise of things becoming nicer will come on Wednesday, or the realization of that promise rather. So what I'll do now is I'll return your homeworks.